Hi, my name is Brian Caffo, and this is the lecture on some common distributions in the Statistical Inference Coursera class in the Data Science series. This class is co-taught with my collaborators Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so in this lecture we're going to cover a handful of common distributions, the most common distributions. The first one, maybe the easiest one, is the so-called Bernoulli distribution named after Jacob Bernoulli. There were a lot of Bernoullis. I think it was Jacob. There were several Bernoulli mathematicians. Let's see. So how the Bernoulli distribution arises is it's the result of a binary outcome. Like, think of a coin flip, basically. We're not necessarily, the coin doesn't have to be fair, right? So we could say that the probabilities are p and 1 minus p. And I know I don't like this because we try to represent unknown parameters with a Greek letter usually, like theta and 1 minus theta, but people use p so often in the Bernoulli distribution case that we're going to stick with it in this case. But notice we're kind of breaking with our convention at this point. So the probability mass function for a Bernoulli random variable is just probability x takes on realized value little x is p to the x 1 minus p to the 1 minus x. It's a pretty kind of boneheaded density, right? So if probability x equals 1 is p to the 1, 1 minus p to the 1 minus 1, it's p, and probability x equals 0 is p to the 0, 1 minus p to the 1 minus 0 equals 1 minus p. Okay? And there's a specific reason why we write it that way, and we'll show you that in a little bit. So the mean of a Bernoulli random variable is p, and the variance is p times 1 minus p. So remember that formula, especially p times 1 minus p, because it comes up a lot. So if we let x be a Bernoulli random variable, it's typical to call x equal to 1 a success, regardless of whether or not what you're measuring is something successful. So the collection of suppose we observe a collection of Bernoullis that are independent and identically distributed, having the same success probability. Then suppose we want to look at, let's say n is 4, and we want to look at the probability of getting a 1, and then a 1, and then a 0, and then a 0. Or the probability of a 1, 0, 1, and 0. Well, that works out to be just by independence, we can take the product of the mass functions. And so here's that equation. It turns out it works out only to be dependent on the number of successes and the number of failures. So these two probabilities are going to be the same, whether it's a 1 and then a 0 and then a 1 and then a 0, or 1, 1, 0, 0, because the number of successes is 2 in both cases and the number of failures is 2 in both cases. This idea of looking at the joint mass function and thinking of it not as a function of x, right? So this joint mass function does this, right? If you plug in a series of zeros and ones, it gives you the associated probability. But if we think of it as not as a function of x, but as a function of p, then it's the so-called likelihood. And the likelihood is a function that, if you look at p, it will kind of be more peaked at values of p that are better supported given the data. And so, of course, the value of p where it achieves its maximum is clearly very important, and that's the so-called maximum likelihood estimate. And in this case, the maximum likelihood estimate works out to be the sample proportion, which is good. We would not believe maximum likelihood if the sample proportion didn't wind up being the best estimate of the population proportion. Okay, and notice an interesting fact. We don't actually have to know all the successes and failures in the order they arrived in. All we need to know is how many successes we had and how many failures we had, and the likelihood is equivalent for all the different values of that. That's the property so-called sufficiency. So let's, just to illustrate this, let's plot all possible likelihoods for small n. So in this case, n is 5. I'm going to pick the values of p that I intend to plot. So just pick between 0 and 1, 1,000 values. I'm going to create an empty plot. This text just is some labeling. I'll show you in the next slide where that pops up. And then here I just create the likelihood for each of these guys, and I plot them, and then I put a title on it. Okay. So what this basically is, each of these is the so-called likelihood. it's the probability of this collection of ones and zeros, but instead of viewed as a function of the ones and zeros, viewed as a function of this probability. And so it does exactly what you'd hope, right? If you get 0 heads, it's going to be more peaked towards lower values. See, it kind of looks like that. Okay? If you get 1 head, it's peaked more toward kind of values around 1/5, and the MLE is at 0.2, exactly like we would hope. And you can see then as you go on, if you get 2 successes out of 5, it moves over. 3 successes out of 5, it moves over a little bit more. 4 successes out of 5, it moves over a little bit more. And 5 successes out of 5, then it's all the way on the other side. But it also, the likelihood acknowledges the possibility that we could have gotten it could have gotten all 5 successes by chance. So there's still a little bit of likelihood for smaller values of p, but it's more concentrated around the MLE, which is 1 in that case. So that's the likelihood. We'll have an entire lecture on the likelihood, but that's a little bit of foreshadowing. Okay, since we're talking about Bernoulli random variables, we might as well talk about binomial random variables. So binomial random variables are just the sum of Bernoulli random variables, IID Bernoulli random variables. And remember, if we had a Bernoulli random, if we had a collection of Bernoulli random variables, the whether we got 1, 1, 0, 0, or 1, 0, 1, 0, all had the same probability. So the binomial in this case would be 2, and the binomial in that case would be 2, the sum of the Bernoullis. So this gives that probability associated with either of those, right? And then this guy just tells you how many different ways we can allocate the ones and zeros, right? And so that yields the binomial probability, basically saying, oh, well, how many different ways can we pick ones and zeros so that they wind up being 2? And since they all have the same probability, we just have to take the probability and multiply it by that number of ways, and then we'll have the associated binomial probability. So, and that's what it works out to be. And just to remind everyone, in case they've forgotten, this notation n choose x is n factorial over x factorial, n minus x factorial, where n choose 0 is the same as n choose n, which is 1. And that counts the number of ways we can select x items out of n without replacement, disregarding the order of the items. Okay, so let's just kind of go through this in the binomial case, just to remind ourselves, just to show kind of how it works, and then we won't go through a formal proof because it'll be kind of obvious. So consider the probability of getting 6 heads out of 10 coin flips. So the Bernoulli probability of getting 6, say, heads in a row, then 4 tails in a row, or any combination of 6 heads and 4 tails, is this guy right here. Okay. And so we just need to multiply it by this guy, the possible number of ways we can get 6 heads and 4 tails, the possible number of orderings we can have out of that, and that yields our binomial probability. It's the way to think about it is we have kind of 10 locations, and you're sort of picking out of the 10 locations the 6 that have 1s in them, and that just counts the number of different ways you can do that. Okay, here's a kind of silly example. Suppose that a friend has 8 children, 7 of which are girls, and let's forget about twins or any of the kind of obvious complexities that could occur out of a problem like this. So if each gender had an independent 50% probability at each birth, what's the probability of getting 7 or more girls out of 8 births? Okay, well, that's a binomial probability. Here's the probability for 7. Here's the probability for 8. Works out to be about 4%. Here's that calculation just done in R. Works out to be about 4%. The binomial distribution has a R function, of course. It's p binom, and that works out to be about 4%. If you do lower tail equals false, in other words, if you want the upper tail, it's important to note that it does greater than. So it starts counting at 7. So you have to put in 6 here, or any number from 6 to 7, but not including 7, will give you the same answer. But you have to do something slightly lower than 7 and slightly bigger than 6 or bigger, because otherwise Otherwise, if you did p binom and put a 7 in there, it would be calculating a strictly larger than 7 probability, so it would start counting at 8. Okay. Anyway, if you do lower tail equals true, it does less than or equal to. So then this would count 7, 6, 5, 4, 3, 2, 1, 0. If you did lower tail equals false, right, it's going to try and count upper, but this would do 8 then, right? Okay. So when it's the probability x less than or equal to the value you put in if its lower tail equals true, and probably x is greater than the value you put in if lower tail equals false. So remember that. Might seem confusing, but it kind of makes a lot of sense to me because of how, distribution functions and survival functions, that's how they're defined. Here's the likelihood associated with that, right? Here's the MLE, right at 7/8, okay? And, it shows, what you're questioning is, is 0.5 really a valid probability, or is there something going on? Is this person just have a higher predilection for having girls than the sort of law of independent assortment would predict? So that calculation is actually an example of a so-called p-value. We'll talk more about p-values later. Okay, so the normal distribution, if we had to get together and crown a king of all distributions, then there's no contest, right? There's no you could maybe have a contest for which distribution is second in command, but the top distribution, the belle of the ball, the ruler of all distributions is the normal distribution. Because if you have to learn one distribution, learn the normal distribution. So anyway, a random variable is said to follow a normal or Gaussian, named after Gauss, who, by the way, didn't invent the normal distribution, but what the heck, let's call it Gaussian anyway. He used it a lot. He did a lot of the work regarding the distribution early on. So the normal distribution is specified by two parameters, a mean and a variance. Remember, a population mean and a population variance. Okay, and it works out its associated density is that guy. It's basically e to the minus x squared, kind of normalized in the right way, which it looks like it's a bell curve. It's the famous so-called bell curve. So if x is a random variable having this density, then expected value of x is mu, and the variance of x is sigma squared, and we write this x tilde normal mu sigma squared is the notation to denote that the random variable follows a normal distribution. In the particular value when mu equals 0 and sigma equals 1, we call it the standard normal distribution. And the standard normal distribution, the density function is usually labeled a lowercase phi, and the distribution function is usually labeled an uppercase phi. And then standard normal random variables are often labeled z variables. Okay, let's go through some calculations. So here's my z values. I'm going to plot them from -3 to -3, and I'm going to take my z values and just plot the normal density at those z values. And I'm going to put some lines on it to talk about. So, remember that for the standard normal density, sigma equals 1. And so the units we can attribute to the z random variables are standard deviations. So 1 unit on a z random variable is 1 standard deviation from the mean. 2 is 2 standard deviations from the mean. 3 is 3 standard deviations from the mean. -1 is 1 standard deviation below the mean. -2 is 1 standard deviation below the mean. 2 standard deviations below the mean, and so on. Between -1 and +1 standard deviations of the mean, about 68% of the normal distribution lies, and because the normal distribution is symmetric, it's about 34% in either side. That's going from there to there, 1 standard deviation. 2 standard deviations, about 95% lies. Okay, and then 3, and then of course equally allocated into the 2 sides, and then 3 standard deviations, almost all of it, about 99%, lies within 3 standard deviations. And these rules hold not just for the standard normal, but for any normal. You just have to talk, this is as long as you're still talking about 1 standard deviation from the mean. So for example, if we take a non-standard normal, if x is normal mu sigma squared, then about 68% of that distribution, the probability if we grab an x from a normal distribution of that sort is about 68% chance it's going to lie in the interval mu plus or minus 1 sigma. There's about a 95% chance that it's going to lie in the interval mu plus or minus 2 sigma, and about 100% chance it'll lie in the interval mu plus or minus 3 sigma. So it's the same picture, it's just this would be in this unit right here, this 0 would be mu, and this 1 would be mu plus sigma 1 sigma, and that minus 1 would be mu minus sigma, and so on. So the same picture holds for all normal distributions, and that's why the standard normal is so useful, because everything in the normal distribution, it's useful to just talk about standard deviations from the mean, and in the standard normal case, it's the easiest case to talk about that. So these benchmark values are very nice to work with, so you just memorize them. Okay. If x is from a normal mu sigma squared distribution, then standardizing it, x minus mu over sigma is then standard normal, which, it's pretty easy to show, right? Expected value of z is equal to expected value of z of x minus mu over sigma. Pull our 1 over sigma out, expected value of x minus mu, but that's just equal to 1 over sigma. Expected value of x minus mu, which is 0, okay? And then you can do the variance too, right? The variance of z is equal to 1 over sigma squared, variance of x minus mu. But whenever we, shifting a random variable doesn't do anything to its variance, so it's equal to the variance of x, which is sigma squared over sigma squared, which is 1. Okay. So that shows that this random variable, regardless of whether or not x is normal or not, if you take a random variable with mean mu variance sigma squared, x minus mu over sigma is going to have mean 0 variance 1. In addition, if x is normal and you do that, z will also be standard normal. Okay. If z is standard normal, right, and go through the same exercise to prove that we get the moments right for x, if you take mu plus sigma z, then we wind up with something that's non-standard normal with mean mu and variance sigma squared. Turns out the non-standard normal density can just be written as a function of the standard normal density like that. So if you take the standard normal density and plug in x minus mu over sigma and divide the whole thing by sigma, you wind up with the non-standard normal density. You can plug that in and check it yourself, and the standard normal distribution function is just plug in x minus mu over sigma into the standard normal distribution function, and you get now the distribution function for the non-standard normal. Okay, so we already covered this. About 68%, 95%, 99% of the normal density lies within 1, 2, and 3 standard deviations. Negative 1.28, negative 1.645, or negative 1.96, which is right around 2, and negative 2.33 are the 10th, 5th, 2.5th, and 1st percentiles of the standard normal distribution. So what I mean by that is if I wanted to find the point here so that 2.5% of the distribution lied below it and 97.5% lied above it, and I was looking at the standard normal, it would be negative 1.96. Of course, because it's symmetric, right? If I wanted to find the point that 2.5% lied above it and 97.5 lied below it, right, that would be positive 1.96. So that's for the standard normal. And then for the non-standard normal, this point is 1.96 standard deviations above the mean. So this is mu, and this is the point mu plus 1.96 sigma, and this is the point mu, and this is the point mu minus 1.96 sigma. Okay, so remember these benchmarks because they're useful for creating confidence intervals. So let's do a simple question. What's the 95th percentile of a normal mu sigma squared distribution? So if you have R, the quick answer is Q norm, 0.95, mean and SD. Or if you want to do the calculation and revert the calculation back to a standard normal, we want the point x naught so that the probability x less than or equal to x naught is 0.95. Okay, We could standardize both sides of that, and remember, if we take x, subtract mu, and divide by sigma, we get a z random variable. Okay, so we want the this point to be such that the probability of z being less than it is 95%. We know we need the point z naught so that the probability of being larger than it is 5%, and the probability of being smaller than it is 95%. We know just from the previous slide that that point is 1.645. So if we set this equation to be true, then we will have found the x naught, and it works out then to be easy that it's x naught plus mu, x naught equals mu plus sigma times 1.645, which is just a familiar form, right? So if we want the point in a non-standard normal distribution that is the 95th percentile, then we find the 95th percentile of a standard normal distribution, which is 1.645 standard deviations from the mean, and then we just figure out what is 1.645 standard deviations from the mean in the non-standard case, and that gives us the answer. We know the probability that a normal mu sigma squared random variable is two standard. What is the probability that a normal mu sigma squared random variable is two standard deviations above the mean? Well, we already know the answer to that because we've already told you it's about 2.5%. So we know in the standard normal that if we take about 2, 1.96 really, that probability works out to be about 2.5%, and that works out to be about 97.5%. But let's go through the calculations. We want the probability x is greater than mu plus 2 sigma, right? If we standardize x so that it's a z random variable, and we standardize the right-hand side, you wind up see that probability z greater than or equal to 2, and then that's about 2.5%. So this is just mathematically going through showing that the way that quantiles work comparing standard to non-standard normal distributions, that as long as you express everything in standard deviation units of the mean, then it all agrees across any normal distribution, whatever type of non-standard it is or standard. Okay, some other properties. The normal distribution is symmetric and peaked about its mean, so therefore its mean, median, and mode are all equal. The population mean, median, and mode are all equal, not necessarily the sample mean, median, and mode. A constant times a normally distributed random variable is also normally distributed, and you can calculate the mean and variance having had the other parts of this class. Sums of normally distributed random variables are again normally distributed, even if the variables are dependent, provided they're all multivariate normal, then that's fine. Which we don't cover the multivariate normal in this class. Sample means of normally distributed random variables are again normally distributed. With what mean and variance, you can do that. The square of a standard normal random variable follows what's called a chi-squared distribution with 1 degree of freedom. And then the sum of independent chi-squareds just adds up the degrees of freedom. So the sum of 2 independent chi-squareds is of degree of freedom 1 is a chi-squared with degree of freedom 2. The exponent of e to the x, if x is a normal, is a so-called log normal random variable. And then, as we'll see later, many random variables, if we normalize them in the right way, limit to a normal distribution. So that's why it's king of all distributions. That, I think, probably this property is what makes the normal distribution top dog. So on normal likelihoods, again, we'll cover likelihoods more in greater detail later on. But remember, the density evaluated as a function of the parameters is the so-called likelihood, and that the points in which the likelihood is maximized turn out to be good estimators. Well, the maximum likelihood estimator for mu turns out to be x bar, as we hoped. The MLE for sigma squared, it works out to be this, sigma squared hat, which is exactly the sample variance, but instead of dividing by n minus 1, it's divided by n. So we actually do not use the MLE when we estimate the variance. We typically use the kind of an unbiased version of the MLE. So that's a little obnoxious, but probably this point doesn't matter for you. Just always use the unbiased version because that's the kind of standard for everyone at this point. Okay, so let's move on to another very important distribution, maybe not quite so important as the normal distribution, but awfully darn important. Maybe the second most important distribution. I think a compelling case could be made for the Poisson distribution being the second most important distribution. I don't know. I have leanings in that direction. Okay, so the Poisson distribution is used to model counts. The Poisson mass function is this guy, lambda to the x e to the negative lambda all over x factorial, where this is the probability x takes value little x for parameter lambda. And it turns out that lambda is an easy parameter because it's just the mean. Its expected value of x is lambda. But what's interesting about the Poisson random variable is that its variance is also lambda. Well, we knew its variance had to be some function of lambda because the Poisson distribution only depends on the one parameter, but it is kind of neat that it works out that the mean and the variance are equal in this case. And then notice in this case x ranges from 0 to infinity. So you might use Poissons to model counts that are sort of unbounded, right? So however many people show up at a bus stop, sure there's some bound, there's only so many people in the world, but for all intents and purposes that's an unbounded number. You can't really put a number on what the limit of that really is in a meaningful way. Of course it's bounded by the number of total people, but it's kind of conceptually unbounded in a different way than if I flip a coin 5 times and I know I'm going to flip it 5 times. That's a different problem, right? We know that the most number of successes I can get is 5. Whereas if you're modeling how many people show up at a bus stop, then you really kind of don't know a realistic version of what that upper limit would be. So some uses for the Poisson, event time data. If you're counting anything like the number of people that show up at a bus stop, the number of photons that are detected from a nuclear reactor per given unit time, these are all reasonable things to model with Poisson. So radioactive decay is the classic one because you can kind of demonstrate via some limiting arguments that radioactive decay does follow a Poisson distribution. Survival data, it turns out there's this deep connection between a lot of these classic survival analysis models and Poisson models. Survival analysis being modeling the time until some event, classically time until death for looking at diseases. Any kind of unbounded count data you're going to model as Poisson. Contingency tables, so if I collect a bunch of people, collect a bunch of characteristics on them, and just create cross-classified tables of how many people fell into this different classification, that's called a contingency table. And it turns out modeling the counts of contingency tables, you model them with Poisson, usually. And then binomials, which are clearly not Poisson, if you have n being large and p being small, then people tend to model them as Poisson. In fact, people do this so frequently that they don't even bother to mention that they're approximating a binomial with a Poisson. So if you're modeling, say, for example, a disease that's very rare and you have large sample sizes, like what's the, let's suppose you're studying autism and vaccination rates. So the percent of kids with autism is very small. The number of kids that gets vaccinated is very large. So if you were to model the autism rates, you would do it probably more likely with a Poisson than you would with a binomial. I take that example because I saw someone doing that just the other day, that they were studying that question. Okay, so the Poisson derivation this is where it comes from. The Poisson distribution comes about from the so-called Poisson processes, and Poisson processes, if you define like a mean number of events per unit time, you let the kind of a window h that you're looking at be very small, and assume that in that interval of length h, the probability of an event occurring is lambda time h, while the probability of more than one event is negligible. So imagine you're monitoring your best stop. You're saying, I'm going to look at windows of 0.1 second, and then only one person can show up at a time in that 0.1 second. So let's just assume no two people are showing up holding hands or something like that. Everyone's it's a commuter day where everyone's coming by themselves. That if you take a small enough time window, you're only going to get one person showing up to the bus stop at any given time. And then whether or not a person shows up in one interval doesn't impact whether or not a person shows up in another interval. That assumption, maybe all of these for the bus stop example are suspect, but at any rate, these are the underlying assumptions for something to be a Poisson process. And then if you take any interval and you count the number of events that occur in that interval, that's a Poisson random variable. And that's the original derivation of the Poisson random variable through Poisson processes. So I want to emphasize that Poissons are really high. The idea of studying rates and using Poisson is really kind of highly tied together. The lambda parameter from a Poisson is really has a unit, right? So if I'm looking at radioactive decay, right, this is the lambda is the decay per unit time, and t is the number of that many time points that I monitored. So if I wanted to look at radioactive decay per minute, t would be in minutes, and lambda would be the rate per minute. So note, lambda is expected value of x over t is the expected count per unit time, and t is the total monitoring time. So we always use the Poisson distribution this way, where we think of t. Sometimes t is 1, in which case it kind of drops out. But in our heads, we're always thinking of a Poisson random variable as being kind of a model for rates. Here's the Poisson approximation of the binomial if you ever need to use it. We assume that lambda is n times p, and x is a binomial np. Recall we're making lambda np, and n gets large and p gets small, but lambda stays constant. Then you can approximate x as Poisson. Let's do it. So imagine the number of people that show up at a bus stop is Poisson with a mean of 2.5 per hour, and you're watching the bus stop for, oh, I'm sorry, this is not an example of a Poisson approximation of the binomial. This is just a regular Poisson. So we want the number of people that show up at a bus stop is Poisson with a mean of 2.5 people per hour. We watch the bus stop for 4 hours. What's the probability that three or fewer people show up the whole time? That is exactly just a Poisson probability. 3, remembering that when we do p for probability distribution, it does 3 or less, okay, which is what we want, so we put 3 in there. Lambda is 2.5 times the number of hours that we monitored, 4, and that works out to be 1%. Okay, so see how we used it? Lambda was the event per unit time, and t was the number of units of time that we measured. Okay, so there's your Poisson example. Let's go through an example of the Poisson approximating the binomial. We flip a coin with success probability 0.01, so p is small. We flip it 500 times. What's the probability of 2 or fewer successes? So again, p binom 2, size equals 500, prob equals 0.1. Here's the exact calculation. It works out to be 0.12. Here's the Poisson approximation, p Poisson 2, lambda equals 500 times 0.01, right? N times p, and that works out to be 0.1247, so pretty close. Okay, so that's the Poisson approximation of the binomial. So here we just showed you exactly how accurate they were in this specific case. And then in your regression class, you actually cover modeling counts using kind of a Poisson version of regression. So it's a very convenient model, and it's great for modeling things like rates. And I would just say this, I would also mention this Poisson approximation of the binomial is so common that people don't even acknowledge that they're doing it. That it's just sort of done immediately in a lot of applications, particularly certain epidemiological applications. If you're studying something like an infection or something like that that's rare relative to the size of the population you're studying, people just automatically use Poisson approximations.